So I'd like to acknowledge my co-author, Thomas Bengtsson, who works here in San Francisco at Genentech now. He's gone on to better things than academic research. Okay, so basically, particle filters are very successful in low-dimensional systems. I'd like to talk a little bit today about how feasible they are in high-dimensional systems. Peter Jan has already talked a bit about this, and you'll see that, well, I think we have some conflicting views on how this works, and so this remains to be sort of resolved, I think. So there's a lot of recent interest in geophysics for particle filters, the implicit particle filter, equivalent weights for particle filter, and then there are a bunch of related methods that involve weighted samples, including mixture filters that are continually being rediscovered, and there's a weighted ensemble Kalman filter that's in the literature. Okay, so just quickly, notation and terminology. The state is X, observations are Y. Dimensions are denoted by a capital N with a subscript that's whatever variable we're talking about. So NE, for example, is the ensemble size. I'm using the particle filter literature notation where superscripts are ensemble members and subscripts are times. So XIK is the ith member at the kth time. I'll use terms interchangeably. Particle and ensemble member mean the same thing. And when I say sampling, I mean the process of generating particles or ensemble members. Okay, so Peter Jan has already talked a bit about particle filters. There's sequential Monte Carlo methods. Basically, the idea is you want to represent the conditional distribution that you're trying to get to with a weighted sample. A generic problem with particle filters is that unless you have a lot of sufficient number of members, then the maximum weight can get close to 1, and that means you're representing this high-dimensional PDF by a single particle with almost unit weight. You get a poor approximation in that situation. Okay, so I want to go through a little bit more about particle filters, so just to kind of introduce some terminology. I'm not expecting you to see all the math on this page. So basically, particle filters employ sequential importance sampling. So the idea is you begin with a weighted sample at time k minus 1, and then we're going to generate a new sample at time k. We want that sample to come from the conditional distribution. So what we're going to do is we're going to draw new particles from a distribution pi that we can specify. And that distribution is going to depend on the particle at the previous time and the observations. It can depend on those things. And then we have to update the weights in the following way to be consistent with this conditional distribution that we want to get to. We update the weights by taking the weight at the old time and multiplying it by what I'll call an incremental weight. So that's indicated by this tilde on top. And the incremental weight is given by this standard formula that involves things you can calculate plus this distribution pi that you're specifying. Okay, so pi is called a proposal distribution or density, and it may depend on the observations, and it definitely depends on the previous value of that particle. Okay, so I'm going to look at two proposals. The standard proposal is just where you take pi to be the transition density for the dynamics. So that means your particle filter involves simply propagating the members from the old time to the new time under the system dynamics. So it's standard ensemble forecasting if you're an atmospheric scientist. And in that case, you get weights that are given by the likelihood of the observations given that new particle. Okay, so the optimal proposal, the so-called optimal proposal, does something different. It also conditions on the observations. So you draw particles where the probability of this new state it's the probability of the new state given the old state and the observations. Okay, and in this case, the weights become just the likelihood of the observations given the old state. Okay. Okay, so I want to sort of drive home two results, and then I'll talk explore these results a bit more. The first result is that we can have asymptotic results for how the maximum weight behaves as the ensemble size gets big and the size of the system in some sense gets big. So if we define, I keep clicking by the mouse. Okay, if we define a quantity tau squared that's just the variance of the logarithm of these incremental weights, where the expectation is over draws from the joint proposal over the joint for the 2 times k minus 1 and k. So we're going to define tau squared that way. Then the result is that when tau squared is big and the ensemble size is big, then you get the maximum weight, expectation of the maximum weight approaches 1 unless the ensemble size grows exponentially in tau squared. So this is definitely a problem if tau squared is big. Okay, so the key point is this applies to both the standard and the optimal proposal. So the standard, we've known about the application of the standard proposal for some time. There are papers here by Bengtsson, and myself in 2008, and then more recent papers explore this application to the optimal proposal. Okay, so the second result is about actually optimality of the optimal proposal. So in the particle filtering literature, the optimal proposal is considered to be optimal in the sense that it minimizes the variance of these incremental weights over draws of the new particles, okay? And this is basically an easy result because that incremental weight for the optimal proposal is independent of the value of the new particle. So that variance is 0, and you obviously can't do any better than that. But in fact, you can show more, that the optimal proposal minimizes this variance over draws from the joint proposal, from the old time and the new time, okay? So this means that the optimal proposal really does provide a lower bound on the performance of particle filters that use sort of a single step in time, where you take the particle at the old time and you're going to generate a new particle just using the old particle and the observations, okay? So you really cannot do better than the optimal proposal. This means that other particle filters, the equivalent weight and the implicit particle filter, are subject to this same bound on the performance. Okay, so here's the canonical simple test problem. It's something we've already seen a couple of times. It's just a bunch of independent degrees of freedom hooked together in a linear model with noise in the model and noise in the observations. You observe each degree of freedom of the system. We're going to assume all sorts of easy things like the prior covariance is the identity, the system noise is just q squared times the identity, and the observation error is also the identity. So this means that you can trivially write down all the things that you need and you can make some progress. And it lets you illustrate the ideas, okay? So one nice thing is you can directly write down this quantity tau squared for the standard proposal and the optimal proposal. So that's given here. So there are a couple of points I want to make here. First of all is if you stare at this for a little while, you can convince yourself that tau squared for the optimal proposal is always smaller than that for the standard proposal. So this is that lower bound effect. Another thing is that the two proposals, the tau squared only differs when this the system noise q squared is non-zero, okay? So in the limit that there's no noise in the model, then the optimal proposal doesn't do anything for you. And the difference between the optimal proposal and the standard proposals grows monotonically as the system noise becomes bigger and bigger. Finally, if you look at any specific parameter setting, so if we take a squared and q squared to be a half, which is kind of a reasonable parameter setting, then tau squared can be substantially different if you use the optimal proposal. So in this case, it would be reduced by a factor of 5. Since that thing is in the exponent of the ensemble size you need, a factor of 5 really is a huge difference in how well this is going to work in practice. Okay, so this just shows this effect. These are histograms of the maximum weight over many replications of the experiment. There's two columns. The standard proposal is shown on the left, the optimal proposal is shown on the right, and then there's 3 different dimensions of the system, 10, 40, and 160. So you can see that if you fix the ensemble size and increase the dimension of the system, you have this tendency for the maximum weight to approach 1. But if you use the optimal proposal, the same thing is going to happen, but it happens more slowly. So if you look at a given system size, a given system dimension, then the optimal proposal is much better behaved. I'm going to go ahead and skip this one because it just makes the same point again. I want to say a little bit about where this optimality comes from. So let's consider an algorithm an exact algorithm to sequentially sample from this posterior distribution. So we're going to rely on a simple identity that for the joint distribution of the joint conditional distribution. You can just write it like this. And what this says is that to sample from this joint conditional distribution, what you do is you first draw xi at time k minus 1 from this distribution, the old state condition on the new observations, and then you draw xik from this distribution, okay? So what I want to do is compare that to what happens when we do it in the particle filter, okay? So in the particle filter, the proposal we're going to draw from, the joint proposal, if we have resampled at the previous time, so the best we can do is a draw from the posterior the previous time. This is what the joint proposal looks like. So what we've got is, if we put in the optimal proposal here, then with this second term looks the same as the exact way of sampling. But what we're missing is we haven't accounted for the new observations, their effect on the old particles, okay? So this is sort of the fundamental thing that you can't get around no matter how cleverly you choose your proposal, is you haven't fixed those old particles upon which you've based your sampling to account for the new observations. Okay, so just the facts are, the optimal proposal has it can give you dramatic benefits relative to the standard proposal in a given problem. The benefits depend on the system noise, so the bigger the system noise, the bigger the benefits can be. Even given that, you still need the ensemble size that's required still scales exponentially with this quantity tau squared. And this optimal proposal really is optimal in the sense that it gives you a lower bound on how everybody else can perform. Okay, so what's the hope for the future? Here's what I think. One is you can actually go back and regenerate particles at earlier times. So this is an idea from the particle filtering literature that they call block resampling. The problem is it makes drawing from the proposal harder, much harder as you go farther and farther back in time. These asymptotic arguments are still applicable. So block resampling will reduce tau squared, but it won't cure this exponential dependence of ensemble size on tau squared. The second possibility you have is to do some kind of spatial localization where the changes that you make from observations are spatially localized in some way that I don't really know how to do, but this is what makes the ensemble Kalman filter work clearly. So we would like to borrow that idea for particle filters. Okay, thanks for your attention.
Questions?
So I'd like to challenge one conclusion, the last one on the previous slide. Is that what you do, you look at it as not in general enough. So two things there. One of them is, so you only allow position of new particle to depend on position of the old particle, not on the ensemble, the whole ensemble of the old particles. And the other thing is that your asymmetry, so the minimum values that you have in the weights, if you say it's with respect to the joint density, I think we actually need to look at the joint density, the marginal density, and at the end time. That's the joint density that's needed. Yeah, really. And I think about field control, okay, not necessarily helping the smooth those.
Well, but it's clear that the problem with the optimal proposal is that those weights depend on the particle at the previous time. And so they're variable. You inherit variability in the weights from the sampling variability at the previous time. And so you have to think about where those particles at the previous time came from if you want to understand what the limitations of that optimal proposal are. Okay? So I definitely would defend looking at the joint proposal because I think you have to understand these algorithms. What was your first comment? Okay, yes, so you could use more things that's outside of the scope of anything I said, but I would say it's not clear to me that you can, the nice thing about staying in that classical importance sampling framework is you have convergence results that tell you you're converging to Bayes' rule. If you use other particles in there, then I don't know exactly what happens. That's all I would say.